This is the third section of the vectors chapter from FP1, and this is the scalar triple product. Okay, so let's define the scalar triple product probably before we go into what we would use it for. And it involves the cross product and the dot product. And actually what it is it's A dot B cross C. Not sure I underline the cross there. I'm going to underline the C. Okay, so this is called the scalar triple product. Now, there's two ways we can work it out. So two methods. One method would be to find B cross C first, and we'd use determinants to do that. Then do A dot whatever we get. So we then do the dot product. So do the cross bit first because it's in brackets by using determinants, then do A dot whatever we get from that. Or there's another way of doing it, and that is to use all determinants. So if vector A is A1, A2, A3, B, all the B's, so B1, B2, B3, and C is C1, C2, C3, then another way of doing it, A dot B cross C is equal to the determinant of the matrix, or 3 by 3 matrix, where all of the elements are basically each of the vectors. So vector A goes at the top, vector B goes in the second row, and vector C goes at the bottom. So this might be a quicker way of doing it. We could do it either way. So if we find a determinant of that, so purely using determinants, not touching the dot products at all, this is another way of working out the scalar triple product. So you can do it either way. Now, why might we use this? Well, it's useful for working out the volume of a 3D shape called a parallelepiped. Now, parallelepiped, I'll try my best to draw this. It may not look fantastic. So imagine you get a cube. I'm better at drawing cubes like this. So I've got some sort of cube, and what I do is I push the top there. So the top leans over, the bottom stays where it is, but the top leans over. So I'll get this sort of cuboidy type shape, but it's like a parallelogram type shape. So let's try and draw it. So just like the way that we draw a cube, you draw two overlapping rectangles or a cuboid. I'm going to try and draw this by drawing two overlapping parallelograms like this, and then hopefully when we join up the edges, that's going to join down there, that will join there. Okay, that doesn't look too bad. So there, we can work out the volume of that, and this is called a parallelepiped. So like parallel, and it looks like piped on the end, parallelepiped. Yeah, so like this cuboid that's been pushed over. Okay, given that, so we have vector A here, we have B here, and we have C here. Find, okay, so we could use either method. Now for part A, I'm going to use find the cross product of B, C, then do the dot product. On part B, I'm going to use the full determinant method. So let's start by working out B cross C. So that is going to be I, J, K. B is 1, 1, minus 1, and C is 2, 3, 5. Okay, so this is going to be I, 1, minus 1, 3, 5, minus J, 1, minus 1, 2, 5, plus K, 1, 1, 2, 3. Okay, so that will give me, right, so 5 minus 3 will give me 8, so I'll get 8i. Then for the next bit here, I will have 5 minus 2, so 5 plus 2 is 7, and since it's a minus, so minus 7j. And then for the last one here, I will have 3 minus 2, which is 1, so just plus k. Okay, so now I do the dot product with A and B cross C. So that's going to be 3 minus 1, 4. With 8 minus 7, 1. So if I do that, I will get 24, 1 times minus 1, so plus 7, plus 4, so that's 28 plus 7, which is 35. Okay, so I get 35. If I'd used the full determinant method, I would also get 35. Right, so let's now move on to the next one, which is like B dot C cross A. So now I'm just going to use determinants only. Notice that it's the same letters, but instead of A, B, C, like this, A, B, C, it's now A there, B, C. So it's like everything has shifted across by a couple of spaces. Let's see if that makes a difference to answer. Okay, so if I use the full determinant method, I will put vector B at the top, so it's going to be 1, 1, minus 1, and then I will do C, which is going to be 2, 3, 5, and then A, 3, minus 1, 4. Okay, so we write them down in the same order as they are written in the question. B at the top, C in the middle, A at the bottom. Right, so we start with 1, and then we have 3, 5, minus 1, 4, minus, I was going to put plus there, minus 1, so we've now got to this one here. So minus 1, and that will be 2, 5, 3, 4, and then minus 1, and this will be 2, 3, 3, minus 1. Okay, so let's work out what this gives us. So we're going to get 1 times by 12 minus 5, so 12 plus 5, 17. So I've got 1 times by 17. Then minus 1 times by, okay, so here we're going to get 8 minus 15, so minus 7. So minus 1 times by minus 7, or minus 1 times minus 7, and then minus 1 again, and that's going to be times by minus 2 plus 9, so minus 2, minus 9, which is going to be minus 11. Okay, let's see what this gives us. So 17 plus 7, which is 24, plus 11, which gives us 35. Okay, so I've used the full determinant method there, and it's interesting that we get the same answer, so it'd be worth exploring this before we move on to part C. When you've got this, so if we had A dot B cross C, okay, we saw actually from our second example it equaled B dot C cross A, and actually if you just shift the letters across by 1, so in other words you move each one across by 1, which means then the C moves to the front, okay, and then we'll do that a second time as well. What we'll get is C dot, so this will also equal C dot A cross B, and again if you move each one of these across by 1, so move the C to there, the B to there, the A to there, and then the B to the front, then we will get B dot C cross A, which is what we just worked out, wasn't it? Yeah, so this is a special result. These three are always true. And because they get shifted across like this by 1, they go around like in a cycle, we say that the triple product, the triple scalar product is cyclic. Okay, the triple scalar product is cyclic. Okay, because it sort of cycles around each one of the letters, you cycle them around. They're all equal to each other. Right, moving on to part C then. And we have A dot A cross C. So we'll work this out. So we can use either method. Let's use the full determinant method again. So we'll have A at the top, so we'll have 3, negative 1, 4, then 3, negative 1, 4 again, and then C, 2, 3, 5. Okay, so this will equal 3 times by the determinant of minus 1, 4, 3, 5, minus 1 times by determinant of 3, 4, 2, 5, and then plus 4 times by determinant of 3, negative 1, 2, 3. Okay, so let's work this out. I'll just do it all in one go and see if we can get just the 3 numbers in the answer. So we'll have 3 times by, actually let me write it down, 3 times by minus 5 minus 12, which is minus 17. 3 times by minus 17. And then minus 1 is going to become plus. So plus 1 times by. So 15 minus 8, which is 7. And then plus 4 times by 9 minus 2, so 9 plus 2, 11. Right, so what's that? 3 times negative 17, I think that's negative 51, plus 7, plus 44. Let's work that out on the calculator and see what we get. So minus 51 plus 7 plus 44 is 0. Okay, so we get a result of 0. Now this gives us another result. This came out as 0 because the A is repeated. We've got the same vector twice, and any time a vector is repeated in this scalar triple product, it will always be 0. So even if the A was here instead. So if this was A dot C cross A, I would still get 0, because remember, if you swap that around, it's just going to give you a negative instead of a positive. And, well, it's still going to be 0, because it's just going to be like negative 0 instead. Yeah? So this gives us a second result, which we'll write down in the middle here. So if a vector appears twice in the scalar triple product, then it is always equal to 0 whenever the scalar triple product, if we have a vector that appears twice, then it's always equal to 0. So here's an example. So A dot, let's say A cross B equals 0. Actually, I want to add another one there, so I'll put 0 equals 0 at the end. Then let's say you've got A dot B cross A, or and that equals 0, or even if I had like B dot A cross A, and then we know that A cross A is equal to 0 anyway, so that equal to 0. The important thing is that this vector appears twice. It doesn't need to be next to each other. As long as it appears twice, we're always going to get 0 as a result. So two important things there to note: the triple or the scalar triple product. So let's get my words the right way around here. The scalar triple product is cyclic in the right colour, and if we got a vector that appears twice, then it the result's always going to be 0. So the scalar triple product. So here it's saying find the volume of this parallelepiped shown in the figure. Given that O is the origin, so we've got the origin as one of the vertices there. And A, B and C have position vectors A, B and C respectively. The angle between B and C is theta, and the angle between the perpendicular height and vector A is phi. So that's another Greek letter there that you may or may not have come across. Pronounced phi, spelled T-H-I. Okay, now if you want to find the volume of one of these shapes, the volume is given by the area of the base times the height. So I'll write that down first. Volume equals area of base times the height. Now the base is a parallelogram, and we know how to find the area of a parallelogram, so we'll just put area of parallelogram, and we'll times that by h, because that's the height, area of parallelogram, times h. Now the area of the parallelogram, so the parallelogram's this thing here, isn't it? Yeah. And we know how to find the area of one of those. I think I've said that already. So that's going to be just the cross product of B and C. So area of parallelogram, which is the base, is the cross product of those two vectors B and C times by the height. Now, if we look at the height, we can use a little bit of simple trigonometry. So basically, let's draw it out here. There's the height. Here's vector A. We could probably find the length of that, couldn't we? Yeah. And we've got this angle phi here. So this side, the A is like the hypotenuse. This side here is like the adjacent and the opposite. So that means the height is going to be equal to the hypotenuse here times by cos of this angle. Yeah, so the height here is equal to this side, the length of this side, times by the cosine of this angle. So instead of height, let's now write the length of A times by the cosine of phi. Now at this point, we could use the definition for the dot product. Yeah, so if I think of this, so this is how we'd get the dot product. If I call one of the vectors A, so it would be A dot, the other vector normally be A dot B. Let's call the other vector, this one, B cross C. Okay, and then what we want is the length of A times by the length of B, which is basically whatever this is, the cross product of this other vector here. If I rearrange it, what I can get from this is this, which is what I've got, isn't it? B cross C times by A. So, by the way, this is times here. This is not cross, that's times. Equals, or cos theta, or cos phi, equals A dot B cross C. Which means I can replace what I've got, this, which is basically what I've got, I can replace it with this. So that is now equal to, and I can write it as A dot B cross C, or I can write it as B cross C dot A, either way around, because it doesn't matter which way around you do the dot product. So if we write it in alphabetical order, we've got the volume of a parallelepiped is equal to A dot B cross C. And you may recognise that because that is the scalar triple product. Okay, it's the scalar triple product, which is handy, isn't it? The scalar triple product gives us the volume of a parallelepiped. Right, so we need to find the volume of the tetrahedron as shown in the figure here. So again, one of the vertices is the origin. So we have the positions of A, B and C. They will be relative to the origin, and we're given there the vectors there. The angle between B and C is theta, and the angle between the perpendicular height and A is phi. Right, so this goes back to some stuff from GCSE. The volume of a tetrahedron. Now, tetrahedron is basically a pyramid with a triangular base. And the way that we find the volume of a pyramid is we do a third times the area of base, whatever the area of the base is, times by its height. So that's just a special type of pyramid with a triangular base. Now the base is a triangle, so you can see here, okay, there's our base. We know how to find the area of a triangle if I've got those vectors B and C, that area is given by half the size of not A and another vector, that should be B and C. So B cross C, so that we've done that from before. And in the previous example, we also worked out that that height there, using a bit of trigonometry, is going to be the length of the hypotenuse, which is the length of A of like, let's just highlight this right angle triangle using a highlighter. So I'm talking about this right angle triangle here. Yeah, so length of A times by the cosine of the angle, they give me the height. So that's going to be cos phi. There we go, stop writing for a second, not sure why. Okay, so third times area of base, so that's half B cross C times by the height. Now I'm not going to put times in so we don't think it's cross, so that's modulus of A cos phi. Now we can simplify this, we'll get 1/6. Now just like before, do you remember all of this in the previous example we said was A dot B cross C or B cross C dot A. Okay, so it's 1/6 A dot B cross C. Now I didn't do this in the previous example, but it is possible that when we work out the scalar triple product it's negative, so we should put a modulus sign here to ensure that we get a positive number, because we can't have like obviously a negative area, so the volume. So volume of a tetrahedron equals 1/6 modulus triple scalar product. Keep saying triple scalar product. Scalar triple product. There we go. Right, in this example, find the volume of a tetrahedron which has these 4 vertices. Now notice that it doesn't have a vertex at the origin. These are in slightly different places. So how are we going to tackle this one? Now there are 2 ways to do this, and I'm going to show you both. So method number 1 is to actually move all of the vertices so that one of the vertices is at the origin. Okay, so method number 1, move all of the vertices so that one of the vertices is at the origin. Okay, just this way that it avoids sort of messing about working out vectors between points, but I'm going to show you both ways. So what do I mean by that? So let's say, for example, I moved this point, the first one, to 0, 0, 0. So I move one of the vertices to the origin. Now let's call each one A, B, C, D. Now if I'm going, and I could do it with any vertex actually, but I've just picked the first one there. If I'm going to move that point to the origin, it means that the first coordinate goes down by 1, needs to move 1 down. The second coordinate needs to go down by 1, and the last coordinate needs to go up by 1. Okay, so it's just like shifting the shape across now. Every coordinate, every x coordinate or I needs to be shifted down by 1. Every y, or the second coordinate, needs to also be shifted down by 1, and the last one needs to be shifted up by 1. So all I'm doing is moving the shape. It doesn't change its volume. All it does is shift all of the coordinates, like a translation, so that we end up with one of the vertices at the origin. And as I said, it could be any vertex. So basically what I'm doing is I'm applying a translation, and this is a translation of -1, -1, 1, okay, to all of the coordinates. So let's do that, and let's work out what each one of the new points is, and I'll write them at the top here. So here, so -1, -1, +1, -1, -1, then add 1, that'll be -1, and then the last one, -1, -1, +1. So now we've got one of the coordinates at the origin. This can go straight into the formula to allow us to work out the volume of the tetrahedron. Right, so the formula for the volume is going to be, what was it again, 1/6 times the scalar triple product of the three vectors. So that's just going to be 1/6, and then the scalar triple product is going to be the determinant of this. So 1, 3, 0, 2 -1 -1, -1, 3, 6. So that'll be 1/6 of 1, and then -1, -1, 3, 6, and then -3, 2, -1, -1, 6, and then +0, 2, -1, -1, 3. Okay, so carrying on, so we've got 1/6 of, now what we'll have 1 times by -6 plus 3, -6 plus 3, so that's -3, I think, and then -3 times by, so this is going to be 12 plus 12 -1, got to be careful here, 12 -1, which is 11, and then 0 times by, well, there's no point working out those values, I'll do it anyway. So 6 -1, which is 5. Right, so this is 1/6 of the modulus of, now we've basically got -3, -33, which is -36. So you can see why we need the modulus, otherwise we'd end up with a negative volume, which can't happen. So it's a 6 of 36, so 6 cubed units would be the volume. So this method here, what I've done is moved all of the points so that one of them ends up at the origin. Now I could have done it with any of the points, I would have ended up with the same answer. Yeah, so you basically apply a translation. Now method number two requires us to work out the vectors between each point. Okay, so method number 2, find the vectors between each point, or each of the vertices. Okay, so there's my drawing of my tetrahedron, and to find the volume I need these three vectors, so I could call them like A, B and C. Now remember, because they're cyclic, the scalar triple product, it doesn't matter which one I call A, which one I call B and which one I call C. So let's find each one of these vectors. So A to C. So whenever you do these, you could either do, if I was to do this, I could do C minus A, or just work out the jump from A to C. So A to C, that jump, first number goes up by 2, the second one goes down by 1, and the third one goes also down by 1. And then AB, so that will be, first one goes up by 1, second one by 3, third one doesn't change, and the last one AD, A to D, first one goes down by 1, the second goes up by 3, and the last one goes up by 6. Now notice that these vectors here are exactly the same as these, aren't they, when we moved it to the origin. That's why this works. So these vectors we've worked out effectively are the same. A, B, there we go, is that one. A to C, there we go, there's there. A to D is that one. Yeah, so you'll see why this works, because when we put this in, we're going to be doing exactly the same calculation. 1/6 of, so if I put AB at the top, and then AC, and then AD, okay, we can see it's exactly the same. So we're still going to end up with 6 as the volume. So you can use either method. One method is to use a translation to move one of the vertices to the origin and then apply the translation to the other vertices, or work out what the vector is between each of the 3 of the well, not 3 of them, but pick one vertex. So I picked vertex A, and find the vector between A and the other vertices. So AB, AC, AD. We don't need BC, yeah? So we just pick a vertex. Now I could instead have done, let's say if I did B to A, then I would have done B to C and B to D. That fantastic B there. Try that again. So I could have found these vectors, or I could have done let's say C to A, C to B, C to D, or I could have picked D to A, D to B, D to C. Yeah, so you pick a vertex and then find the vectors from that vertex to the other 3 remaining vertices. Okay, you should now be able to do exercise 1C on pages 14 to 16. So before you do that, we'll just do a quick recap of this scalar triple product. Okay, and this scalar triple product is A dot B cross C, which is equal to, we'll shift them across 1, so we'll get C dot A cross B, cycle it across 1 more time, which is equal to B dot C cross A. So the fact that they can all go around like this means that it's cyclic, and the way that we can work that out is we can either do to work out, you can either do cross product first, cross product of B and C if I'm talking about the first one, then do the dot product, or you can use a full determinant method. And if I was going to do a full determinant method, then this represents our vector A, our vector B, our vector C. Okay, and that will equal our scalar triple product. And we can use this scalar triple product to find volumes. And we've done the volumes of two shapes, a parallelepiped and that's the modulus of the scalar triple product. And also we did the tetrahedron, and that's 1/6 of the modulus of the scalar triple product. Okay, so the modulus ensures that we get a positive answer and we get a positive volume.